The Mars Rover missions aim to perform experiments that define the next era of space exploration, researching the history, climate, and geology of Mars as a precursor to human exploration. The Mars 2020 Perseverance rover is currently midway through its 7-month journey to the surface of the red planet. To succeed in its scientific endeavours, the rover must be able to traverse unknown hazardous terrain. The difficulties associated with the challenging Martian terrain have impacted previous rover missions. In 2005, the Opportunity rover became stuck in a sand dune, requiring the consistent efforts of NASA engineers and mission managers over 5 weeks for a successful escape. Similarly, in 2009, the Spirit rover was trapped in an area of sand, and in a compromised position, the solar panels could not provide enough power to the rover, with communication attempts ceasing in 2011. In early 2017, it was also identified that the wheels of the Curiosity rover were suffering damage as a result of driving across pointed bedrock. The process of developing and launching a Mars rover is extremely expensive, with the Curiosity mission costing approximately $2.5 billion. It is evident that a method is required to reduce the rover risk of traversal, enabling safe exploration of the Martian surface. As a result of these motivations, the following research question was developed. How can deep learning be employed for terrain classification as a component of traversability analysis on a Mars rover? The proposed solution consists of an RGBD camera which obtains colour and depth images of the surrounding terrain. A trained CNN performs semantic segmentation on the colour image, yielding pixel-wise class labels identifying each type of terrain. A height map is constructed by the deprojection of the depth image. Based on the rover kinematics, 7 possible motion arcs are defined. The traversability of each path is assessed as a function of the terrain predictions, relative terrain height, local goal, and energy expenditure of a given steering angle. The path with the highest traversability is identified and executed in simulation. This thesis draws on existing work in rover navigation, deep learning, and traversability analysis. Current rover missions employ the Gestalt navigation system, short for Grid-Based Estimation of Surface Traversability, applied to local terrain. The system utilizes stereo vision to develop a geometric analysis of the local surface. The surrounding terrain is discretized into cells, and a traversability score is assigned based on slope, roughness, elevation, and the traversability of neighboring cells. The addition of terrain classification by the application of machine learning is a concept explored in a wide range of applications. Soil property and object classification, also known as SPOC, is a deep learning-based terrain classification for Mars rovers presented by JPL with a focus on landing site traversability analysis. This thesis presents a similar application of deep learning-based terrain classification as an extension to current methods of Mars rover traversability analysis, implemented with rover-specific path planning and control. The conceptualized rover is the SORPY rover, inspired by the JPL open source rover project. Mimicking the structure of the MSL Curiosity rover, SORPY employs rocker bogie suspension. The robust configuration enables the distribution of the payload uniformly across the 6 wheels. The body of the rover is connected by 2 coaxial pivot joints. A differential supports the body, constraining the pitch to keep the body level as the wheels move over uneven terrain. The geometry of the terrain defines the configuration of the rocker bogie mechanism and thus the stability and load distribution on the wheels of the rover. The original parameters for the NASA Mars Exploration Rover missions detail a maximum traversable object height of 20 cm, given a wheel radius of 10 cm. Additionally, a maximum allowable pitch angle of 25 degrees is defined. The SORPY rover wheel has a radius of 6 cm. Applying the same ratio, a traversable height limit of 12 cm is defined, yielding a maximum corresponding pitch of 25 degrees. The candidate motion arcs are defined by the radius of the instantaneous center of rotation, or ICR, to the center of the rover body. Defining a region of interest as 1 meter squared in front of the rover, the radius values of 0.5, 1 meter, and 2 meter are defined on both the left and the right. A central path indicating linear rover motion is also defined. Considering the angle subtended by the arc of a given radius and time for path execution, an angular velocity of the rover is defined. The Ackermann geometry accounts for the difference in steering angle for each wheel given a common instantaneous center of rotation. As the rover turns about the ICR, The inner and outer wheels operate with independent angles and velocities. The linear rover velocity is then calculated as a product of the angular velocity and the radius of the turn. Based on the position of each wheel relative to the ICR, each wheel velocity and angle is solved and utilized as the input parameters in simulation. The coordinate reference frames are considered. The pixel in the image frame is converted to the camera frame using the intrinsic camera parameters. A transformation matrix then defines the translation and rotation between frames. The camera, tilt, pan, rover body, and local ground reference frame are then compounded, yielding the image point in the 3D local ground coordinates. This local ground reference frame is defined with respect to the position of the rover body. The traversability estimation algorithm is implemented in Python code with distinct modules for the RGBD camera, terrain classification, height analysis, path definitions, traversability analysis, rover display, and rover motion. The system is configured with a ROS interface such that the SORPY rover motion is exhibited in a gazebo simulation. A 2D height map is constructed by applying the coordinate transforms discussed on the depth image data, corresponding to the color image shown. As the camera height, pan, and tilt parameters are known, the 3D coordinates of each point in the image can be mapped to the local ground coordinates. A region of interest of 1 meter squared in front of the rover is defined, such that the height of obstacles directly in front of the rover can be assessed. In addition to height analysis, this thesis introduces terrain classification by semantic segmentation. Semantic segmentation, as an application of deep learning, classifies each pixel within an image, chosen over alternative deep learning methods such as object detection and instance segmentation, as we require the terrain classification of irregular shaped features at specific locations. This process of semantic segmentation first requires a dataset for training, validating, and testing the model. The Museum of Arts and Applied Sciences Mars Lab yields an area of simulated Martian terrain, created with an emphasis on scientific accuracy. Color and depth images were obtained with the RealSense D435 RGBD camera at both the Mars Lab and an outdoor testing site at the Yarramalong bike track, due to the presence of dirt and rocks that align with the terrain expected on Mars. Images were captured with a resolution of 640 by 480 pixels. The RGB images were labelled using the MATLAB image labeler, producing a raw dataset of 153 images and corresponding labels. Each image and label was then cropped into two 480 by 480 segments and resized to 224 by 224 pixels. The dataset is split into 70% training, 25% validation, and 5% testing data. Due to the relatively small dataset, image augmentation was implemented to avoid overfitting by introducing random variation in brightness, contrast, saturation, scale, reflection, and rotation. Google Colab was utilized for training the convolutional neural network, as it provides access to powerful GPU hardware accelerators that drastically reduce training times. The loss function defines the mathematical approach to evaluate performance and respond, improving the model. Several loss functions were implemented and compared, with categorical focal dice loss producing the greatest results. By combining focal and dice loss, common class instances are downweighted such that greater importance is placed on less frequent classes. This is suitable for the imbalanced dataset and is successful as it does not produce large fluctuations or destabilize training. Several model architectures were implemented to compare their performance in classifying terrain as small rocks, compact dirt, large rocks, walls, or objects. The semantic architectures of SegNet and UNet were selected, implemented with bases VGG16, VGG19, ResNet50, and MobileNet. The analysis of class-wise metrics indicate the success of both UNet ResNet50 and SegNet VGG16. The SegNet VGG16 model is selected. This architecture implements a symmetrical encoder-decoder structure and yields a validation accuracy of 85.54, an F1 score of 83.53, and an intersection over union of 73.7. when trained over 50 epochs with categorical focal dice loss. The summarized confusion matrix is presented based on the model performance on the testing dataset. The strength of the diagonals indicate the success of inference, with some misclassifications occurring between the classes of small rocks and compact dirt. This is expected due to the indefinite boundaries of regions of small rocks and their visual similarity to compact dirt in many instances. Some examples of the predictions of the train network on testing data obtained from the Mars lab and the terrestrial testing site are shown. It is evident that the output is satisfactory in predicting the correct terrain classes, producing clear boundaries to most regions, which are vital for the rover traversability estimation algorithm. As an extension, the performance of the model is challenged to produce predictions on true Martian terrain. The classes of compact dirt, large rocks, and small rocks are clearly identified. The CNN is trained only on data obtained from the MAAS Mars lab and the outdoor testing site. Thus, the successful inference on real Mars terrain verifies the developed method of deep learning for Mars terrain classification. The traversability estimation algorithm brings all the previous components together to form an assessment of the risk of rover motion. For each waypoint along a possible motion arc, the cost defined by the measures of class, height, proximity to a local goal, and the steering angle is incorporated into a cumulative traversability score. This path with the lowest risk is identified and the corresponding wheel velocities and angles are output to the rover simulation interface. The rover display shows the input image, segmentation output, height map, and the path selected. The simulated rover then moves along the arc for a period of 10 seconds. At the conclusion, this process is repeated, exhibiting autonomous traversability analysis, path planning, and rover control. The performance of the integrated system is further demonstrated by defining an area of simulated Martian terrain within the testing site. The starting position and end goal are defined, and the tripod is physically repositioned based on the selected path output. This experiment highlights the success of the integrated system, navigating obstacles to reach the goal in just 11 motion arcs. Overall, this thesis contributes an implementation of deep learning for terrain classification, a traversability estimation algorithm for extended risk assessment, and path planning and control of a Mars rover, exhibited in simulation. In producing these contributions, the detailed system design enables future works to extend on the presented solution. Some of the areas for future development include extending the dataset for improved classification, building on the measures of traversability, and employing the traversability estimation algorithm on a physical rover. As humans strive to explore the universe and unlock the secrets of Mars, safe, reliable rover traversal is the key to obtaining the scientific data we require. Thank you for listening.